All right, let's dive into a really fun one today. We're going to deconstruct a pretty challenging problem from a linear algebra exam. You know the type? It's one of those multi-part questions that just looks intimidating on the page. But I promise you, by the time we're done here, you'll see it's actually a great chance to connect some super important concepts.
So the real question is, how do you take a question that looks daunting and turn it into a moment where you can really shine? Well, it's all about shifting your mindset, right? We're not just going to hunt for an answer. Nope, we're going to build a strategy, break this thing down piece by piece, and turn it from a headache into a showcase for what you know.
Okay, so here's our game plan. First, we'll look at the challenge itself, question 6. Then we'll crack the matrix mystery in part A. After that, we'll uncover the transformation secret in part B, and we'll wrap it all up with a strategic toolkit you can take with you. Let's do this.
So here it is, question 6. Think of it as a classic two-part puzzle. You've got part A, which is all about a specific matrix with a tricky, complex variable inside. Then part B gets a little more abstract, asking us about the properties of a linear transformation. Now, they might look totally different at first glance, but you'll see they're both unlocked with the exact same kind of strategic thinking.
All right, let's dive into part A, the matrix mystery. Our mission, should we choose to accept it, is to take this matrix and figure out the exact values of a complex number z that make it do something very, very specific.
And here's our main suspect, matrix A. Take a look. See how that variable z is just sprinkled all over the place? Our job is to figure out exactly which values of z are going to crack this case wide open. Okay, now this is the core clue. The question lays out a very specific condition. The matrix has to have a rank less than 3. Now listen, that's not just a calculation instruction, it's a property. And that one little phrase is everything. It's the key that points us directly to the exact tool we need.
And what is that tool? Well, it's the rank determinant theorem. This is a game changer. Basically, it says that for any square matrix, its rank is less than its full size if and only if its determinant is 0. So for our 3x3 matrix, this theorem is our master key. When the question says rank less than 3, it's really just a secret code for the determinant is 0.
So let's connect those dots, right? We have a condition about rank. We have a theorem that translates that condition into something we can actually calculate. So what does that mean we have to do next?
It means this. We just took a kind of abstract problem about rank and turned it into a super concrete task. Just calculate the determinant and set it to 0. That's it. Now all we have to do is solve that equation for z. That is a massive step forward.
Okay, so calculating the determinant. Now, look, we could just brute force this thing, but why would we? There's a much smarter way. Check out the first two rows. They both start with z minus 4. That's not a coincidence, that's a gift. If we just subtract the first row from the second, bam, we get a 0 in that second row. And you know what that means? Expanding the determinant along a row with the 0 in it makes our lives so much easier. After that, it's just a matter of expanding, factoring, and solving.
And after we do all that, a little simplification, a little expanding, some factoring, we land on this beautiful, simple equation. I mean, look at that. We boiled that whole messy matrix down to this one clean expression. The solutions are literally just staring us in the face now. And there you have it. The values of z that crack our mystery are 1, 2, and 4. Seriously, if you plug any of those numbers back into that original matrix, I guarantee you its determinant will be 0 and its rank will be less than 3. So, part A, solved. Now, let's see what part B is all about. Okay, part B. We're shifting gears a little bit here. We're moving away from a concrete matrix and into the more abstract world of linear transformations. But, and this is the cool part, just like in part A, this entire problem hinges on one single central clue that unlocks everything. And here is that clue, t squared equals 2t. This little equation, you can think of it like the DNA of our transformation. It literally contains all the genetic information we need to figure out t's eigenvalues and all its core properties. Oh, and they also tell us that t isn't the 0 transformation, which might seem like a throwaway detail, but trust me, it's absolutely crucial.
So let's play with this equation a bit. If we rearrange it, we get t times the quantity t minus 2 times the identity equals 0. Now that should look really familiar, right? It looks just like a factored polynomial from high school algebra. And in linear algebra, when you see an equation like this, it's telling you something really profound about the transformation's possible eigenvalue.
Okay, so that equation tells us the only possible eigenvalues for t are 0 and 2. Now let's think about this. What does it even mean for a transformation to be invertible? Well, for one, it can't have an eigenvalue of 0. Why not? Because an eigenvalue of 0 means there's some non-zero vector out there that t just squishes down to the 0 vector. That whole collection of vectors that get squished is called the kernel. And if the kernel has anything in it besides the 0 vector itself, the transformation is not invertible, period. The problem actually wants us to prove t is not invertible, so our goal is to show that 0 absolutely has to be one of its eigenvalues. So let's put our detective work together. What have we deduced? Well, the only possible eigenvalues are 0 and 2. We know t isn't the 0 map, which means 2 must be an eigenvalue. And since we have to prove it's not invertible, that means 0 must also be an eigenvalue. And this is the real jackpot, because having 2 distinct eigenvalues in a 2-dimensional space is a golden ticket. It guarantees that t is diagonalizable. Why? Because the eigenvectors that go with those eigenvalues will be linearly independent, which means they can form a basis for the whole space. I mean, that is a massive insight, all from one simple equation. And this whole line of thinking leads us straight to another superstar theorem, the rank nullity theorem. It just says that the dimension of your starting space, your domain, is equal to the dimension of your output space, the image, plus the dimension of that space that gets squished to 0, the kernel. So for us, our domain is r squared, dimension 2. Since 0 is an eigenvalue, we know the kernel isn't trivial, so its dimension has to be at least 1. And since 2 is an eigenvalue, the image isn't trivial either, so its dimension is also at least 1. So how can two numbers that are both at least 1 add up to 2? Well, there's only one way. They both have to be 1.
Okay, last piece of the puzzle. We need to build a special basis, let's call it B. And the strategy is pretty straightforward. Find an eigenvector for each eigenvalue. So first, we just grab any non-zero vector, v1, from the kernel. By definition, that's an eigenvector for our eigenvalue 0. Easy. Next, we grab a non-zero vector, v2, from the image. And here's where it gets really cool. Because v2 is in the image, we know it's the output of t acting on some other vector. Let's call it w. So what happens if we apply t to our v2? We get t of w, which is just t squared of w. But wait, remember our central clue? T squared equals 2t. So t squared of w is just 2 times t of w. And what is t of w? It's our vector v2. So we just proved that t of v2 equals 2 times v2. Boom. It's an eigenvector for the eigenvalue 2.
And so we arrive at the grand finale. When we write the matrix for our transformation t, using this special basis B that we just built, look what we get. It becomes this beautifully simple diagonal matrix. Just our eigenvalues, 0 and 2, sitting right there on the diagonal. This is a perfect illustration of a core idea in linear algebra. Choosing the right perspective, the right basis, can take something that seems complicated and reveal its true, simple nature.
All right, we did it. We solved the problem. But honestly, the answer itself isn't the most important part. The real takeaway here is the strategy. So let's zoom out and distill everything we just did into a toolkit that you can carry with you to any other problem.
So here are the key tools for your linear algebra toolkit. First, if a problem ever mentions rank less than n, your brain should immediately scream determinant equals 0. Second, if you ever see a polynomial equation with a transformation in it, like our t squared equals 2t, you should immediately start thinking about eigenvalues. Third, if the goal is to get a nice simple diagonal matrix, you know the tool for that job is finding a basis of eigenvectors. And finally, never forget the rank nullity theorem. It's the essential bridge that connects a transformation's image and its kernel. So, the next time you're staring down a really complex exam question, just remember these strategies. It's not about memorizing a million different solutions. It's about knowing which key fits which lock. It's about having the right tools to unlock the problem. So, what hard question are you going to make look easy next time?